think most people are here. We're going to finish 4.3 today, one way or another. So what I've got here is a kind of summary of the 4 main kinds of questions. The one at the bottom, these questions here, all to do with graphs. Right, here's a graph, tell me when it's increasing. Here's a derivative graph, tell me, you know, when it's increasing, whatever it might be. So we're not going to do any more of those. Those are ones you've covered, I think. We're going to basically do 3 kinds of questions today. We're going to do ones where you're given a function and you're going to find intervals where it increases, decreases. There you go. Local min value and local max. And then we're going to do some questions where we do concave up, concave down, and inflection points. When we do these questions, isn't it going to be the first derivative that we use? And when you want to find concave up or concave down or inflection points, as in these 3 questions, it's going to be the second derivative that you use. And then there's 3 questions where you do everything. And everything means you find increasing, decreasing, max and min, concave up, concave down, and inflection points, and pretty much everything you would ever want to know about a function. And there are 3 questions in the homework that get you to do that. So let's return back to this one. And we are being asked to find when is it increasing, decreasing, the local min value and the local max value. So first thing you're going to do is you're going to find the derivative. So it's a power rule. Now, after you find the derivative, you need to do one more thing. You need to do style points on these guys. Now, normally that would be a totally acceptable answer for polynomials at least, but we want it to be factored. So I'm talking style points here. I really just mean factor the heck out of everything. So whenever you get a first derivative, factor it till you can factor it no more. Can you see a common factor that I can take out of this quadratic?
6.
Now that leaves me with that one. And do you also, I hope, recognize that this quadratic can be factored? So what are the combinations that work for this one?
+5 - 2.
So that's basically step 1. The next step in this process, what I'm going to call step 2, is you find the critical numbers. The critical numbers are when the derivative is 0 or when it is undefined. In this question, I don't need to worry about undefined, so I only need to find the critical numbers, which are basically when is this derivative 0. Now, because I've done the style points, isn't finding when this 0 very easy. It's going to happen at 2 locations. And these are our 2 critical numbers. So step 3 is we do a number line. And on this number line, I'm going to make sure that I've got -5 in it. And this number line is going to have information about the first derivative. So at x -5, the derivative is 0. And at x equals 2, the derivative is 0. And those little arrows mean that the function continues in both directions forever. And I do step 4. Step 4 is test points. So when you find the critical numbers, can you imagine that it separates the number line like little invisible walls into three regions? I'll call this region A, this region here, I'll call it B, and this guy at the end, I'll call it C. So there are three distinct regions. And when I say pick test points, what I'm looking for here is a value of X in region A, a different test point in region B, and a third one in C. Well, over here, I think I'm going to pick -6. Anything between here and here is good. I'm going to pick 0 and then pick 3. Now, for each one of these test points, so for -6, for 0, and for 3, I find out what its derivative is equal to. And I don't care if the answer is +44 or +4. I really only care is it positive. Because of that, I can do a shortcut. So -6. 6 is positive. -6 add 5 is negative. -6 take away 2 is negative. Those three together give me a positive answer. Do you see how I found the answer is positive without worrying about numerical value? Right, now if you plug in 0, positive, positive, negative. And if you plug in 3, positive, 3 plus 5 is positive, and 3 take away 2 is positive, and 3 positive things give me positives. So I now know that it's positive in this region. Everybody in the middle is negative derivative and positive at the end. And that is us virtually finished. Because once you've created this number line with all the pluses and minuses, you can answer any of these 4 questions here. Right. So I'll move over because I need some room. And I would like to know the interval of x's, right? The values of x's where it is increasing. It's increasing when the derivative is positive. So that's -infinity up to an x value -5, union, and it's positive over here. So from 2 to infinity. And I've been told that you can use the U symbol in WebAssign. It's in one of the submenus, so you can actually get it. And now we have decreasing, which happens basically between here and here. So what's -5 to 2? Now, we've been asked to find the local min value and the local max value. If I go to this critical number and we look at what's going on here, it's positive. That means it's positive, it's going up the way. Then it's 0 derivative, so it's flat lines, and then it's negative. Doesn't that tell me I have a local maximum at -5? See by its shape, right? Up, along, and down. Now, a local maximum at -5, then I just need to find the value of the function at -5. And I don't know what the value of that function is, so I'm going to have to calculate it now. 2 times -5 cubed, add 9 times -5 squared, take away 60 times brackets -5, and I get the answer. Oops. $2.75. Okay. What's happening at 2? At x equals 2. Well, on the left, the derivative is negative, so the function's going down the way. Then it's 0, then it's 4. So that's local min. So all I need to do is find this function at 2. 2, 4, 8, 16. 16 add 36 is 52. 52 take away 120 is -63, or at least what I think it is in my head, so we'll call it that. And that is from start to finish Oops, got it on one page. How to find increasing, decreasing local max and min of a polynomial. And they take a long time, took 10 minutes. So you know that these questions are not going to be short. So what I'm going to show you next is another example of that. That was a polynomial. This time I'm going to do a fractional value, a rational value. And the reason I want to do this is that the algebra is a little bit different. What rule shall I use to differentiate this function?
Product.
Agreed. That's f, this is g, right? So I'm going to go f dash g plus f of g dashed. If you differentiate this guy, it's multiplied by the power and then reduce the power by 1. Leave the second guy alone. Leave the first guy alone and differentiate the second guy. And this is where the fun starts. Style points. This thing factors. It's not a natural factor. In fact, it looks unnatural, but nonetheless, it has a common factor. They both contain fractional powers of x. What is the common factor between x to the power of negative 1/3 and x to the power of 2/3? Which one of those two is the common factor?
Negative 1/3.
And that's just the beginning of your headache. Right, pull out negative 1/3, that's easy. What does that leave behind? It leaves 2/3 x minus 6. I guess I can live with that. Now, what's going to happen when you pull out a negative 1/3 from positive 2/3? And this is weird, but it's correct.
It should just give you x.
It should just give you x. Because taking away a negative is like adding 1/3. 2/3 add 1/3, 3/3, you get 1. Now, that negative power is going to come downstairs, and this is going to be 2/3 x take away 4 plus an x. And now I have 5/3 x take away 4 over x to the 1/3. Do you see how ugly that derivative is? But technically that is style points. That guy is much nicer looking than that. I can't do any more than that. So let me figure out where the critical numbers are. Well, if you solve when is the derivative 0, you're really trying to solve when is this thing equal to 0. And that only matters when the top is 0. I don't care what the bottom is, it doesn't affect the answer, doesn't matter. If I add 4 to both sides and then do the rest, there's my first critical number. There are also critical numbers when a function is undefined. Is there any value of x that you would have problems finding the derivative of? What's the
0.
one value of x? I think I've got 0. So my number line will look something like this. Here's 0, here's -1, and it goes on forever. And I'm going to go, what's that, 5? That's 2 2/5. So I go 1, I go 2, I go 3, and 2 2/5 is kind of sort of about there. and the other one just kind of bit there. And on this one, I just remind myself it's undefined, and this one it's 0. And then I would do test points. So you can imagine a little invisible wall. There's a region A, a region B, and a region C. What would be a good test point for region A?
-1.
Yeah. How about region B?
One.
What would be, yeah, or 2 if you like. And I'm picking 3. Right? I'm just going to tell you the answer and you're just going to check it later. But if you plug -1 into the derivative function, right, which is this guy here, if you plug -1 into this, the answer ends up being positive. If you plug 1 into this, the answer is negative. And if you plug 3 into this, the answer is positive. So I now know that this is plus, that these are negatives, and that this is plus. And I'm going to stop here because we don't have a lot of time to finish every question because they take so long. But once you've got this, can't you tell increasing, decreasing, right? Can't you figure them out? Don't you know that there's a local max or local min probably happening at these 2 points? And you can figure out what the y coordinate is by plugging in here. There's probably some ugly answer, but it does exist. So that's basically how you would tackle rational functions. Do a trig one. In the trig functions, they almost always restrict the x values to 1 cycle. Otherwise, you end up with an infinite number of answers. This one doesn't look like much of a derivative. You get 3 cosine x's, take away 3 sine x's. I guess I could pull out a 3 as a common factor, but that's not going to make much difference. So let's look for critical numbers, and that's where the fun starts. I want to find out when the derivative is 0, because I know I don't need to worry about undefined. I need to solve that trig equation. In 142, right, trig 142, you solved some trig equations. And it's probably been a while since you've had to solve one. So let's go. Tell me what to do to both sides. That silence is scary. You did trig. I know you did trig because you couldn't get into this class if you haven't done trig. And I know you'd solved equations because I solve equations when I teach it. But you can't remember. Come on. I could tell you, but if I tell you, you just forget. If you remember, it's in your head. You've sucked it out. What can I do to both sides to get this to look a little bit prettier?
Would you just want to move the 3 sine x over?
Good start. Sometimes you just have to do the first step and then something comes to you. What do you think I'm going to do to both sides now?
Take turn.
I didn't catch
No.
that.
I mean, sorry, divide by 3.
Okay, I can divide by 3. You're getting closer. Divide both sides by 3, the 3's disappear. Right? Come on, one more step and you're there. I'm you know, putting you under pressure here, but you know, let's fight this through. Do something to both sides so that there's only one trig.
Divide
Right.
by cosine.
Yes. And that's 1, and that's tan x. Now all you need to do is tell me what values of x have a tangent of 1, right? What angles have a tangent of 1? There's actually 2. There's one in the first quadrant, and then there's another one in one of the other quadrants. Does anybody know what angle has a tangent of 1? What angle has a tangent of 1?
Matthew said in,
Corwin?
sorry, pi over 4 and 5 pi over 4.
There you go, guys. First quadrant, third quadrant. Right, moral of this story is anything you've learned from Math 99 onwards, anything you've learned is going to come up somewhere in your calc world. Haven't we already factored the quadratic? Right, that's from what, Math 99? And here we're doing some trig 2. Right, from this guy, you start at 0, you finish at 2 pi. I guess that's, well, that's pi there. Right. Pi upon 2 here. 3 upon 2 pi here, and then plug in the quarters. At 1/4, which is here, the derivative is 0. And at 5/4, which would be here, the derivative is 0. And then you do test points, and you do pluses and minuses and all the other stuff. But basically, hopefully you know how to fill this in. If I was going to do test points, I would do 0, pi, and I would do 2 pi. Let's see, if I plug in 0 into the derivative, it's positive, that's negative, and then it's back to being positive. And that would be how to take care of a trig one. Now, I can imagine what's going to happen is you're going to hit a point like this. And if you don't know how to solve a trig equation, then that's it. You're just going to say, I'm stuck. And if you can fight your way through it, then you will get the answer. So let's do an example of a rational function, or at least part of that question, because you notice I'm not finishing them. This one is like question 9. Would you agree this is just a quotient rule, nothing that special? Pops an F, bottom's a G, F dash G, take away F of G dashed over G squared. Differentiate the top, you get 2x, leave the G alone, leave the F alone, differentiate the G, square the bottom. Distribute. 2x squared, take away 6x, take away an x squared, add an 8. X squared, take away 6x, add 8. There we go. Looking pretty. But not as pretty as it has to be. Can we do anything else to make this even nicer looking? Math 99. Can you see anything that we can do to the top that could make this nicer? Yes. And what's the factors?
-4, -2.
If you factor the derivative, isn't it going to be really easy to find the critical numbers? This particular derivative, doesn't it have 3 critical numbers? What are the 3 critical numbers for this derivative?
2, 4, and 0. Or 0,
2 and
2,
4.
and 4.
Well,
I mean,
2.
sorry. See, no. 3.
Yes,
2,
2,
3,
4,
and 4.
and 2, 3, 4, right. Now, at 2 and 4 isn't the derivative 0, and at 3 it has a problem. It's undefined. Now, can you imagine me doing a number line, putting in 2, 3, and 4, picking test points, doing all the plus minus stuff, finding out where it's increasing and it's decreasing, and a whole load of other stuff that would take another 5 to 10 minutes. So what we're going to do next is we are going to do these guys. Concave up, concave down, and inflection points. So I'm just finding one to do it to. I'm going to do it question 13. And the function that we're being asked to find, when is it concave up, when is it concave down, and its inflection points, is this ugly guy. If you want to find anything to do with things like concave up and concave down, it's the second derivative that we need. So I'm going to find the first derivative and then move straight on to the second derivative after that. This guy is a chain rule. It's a log of something. So it's 1 over something times the derivative of that something. So the first derivative is cosine x all over 2 plus sine x. Now to find its second derivative, I'm going to differentiate this fella, and this becomes a quotient rule question. If you differentiate the top, you get negative sine x. Leave the bottom alone. Take away, leave the top alone, and differentiate that guy. And then we have the whole thing on the bottom squared. If I distribute, I get negative 2 sine x. Take away a sine squared x. Take away a cos squared x. All over that guy. There is a lot, well, maybe not a lot, but there is still some more I can do to make this prettier. What does negative sine squared, negative cos squared x become? It's a trig identity. What is it equal to?
-1.
Great. So it's, again, it's not a lot of improvement, but every little bit helps. Agreed? And that's as good as that's going to get. So that's style points finished. Now let's look for critical numbers. I need to find out when the second derivative is 0, which means I need to basically solve this puzzle. A fraction will equal 0 only when the top is 0, so I can ignore the bottom. And we have a trig equation. A little bit different from the first trig equation, but still a trig one. What am I going to do to both sides to get closer to solving this one?
Add 1 and then divide by -2.
Yeah, I think it's a kind of, you haven't done it for a while, but once you start doing it, doesn't it all come back to you? Right. Now I'm looking for two angles in the unit circle where the sine is -1. And isn't that going to be in the third and fourth quadrants? Agreed? What angle has a sine of -1/2 then? There's two of them. Just give me any one of the two. One's in the third quadrant, the other's in the fourth. And if you've got your unit circle somewhere handy, you should be able to read it off. Anybody got it at the top of their tongue or whatever?
Matthew says in chat 7 pi over 6.
Well done. And what's the other one? There's one more. It's in the fourth quadrant.
11 pi over 6.
We have nailed it. Well done. We got it. So my number line that I'm now going to create is going to start at 0 and it's going to finish at 2 pi. And the reason for that is that the original question told me to. And then I guess in the middle, I have got, I know it's not really 6, it's pi, but I'm doing everything in multiples of 6. So 1, 2, 3, 4, 5, 6. There's 7, 6, 7, 8, 9, 10, 11, 6. Might not be quite to scale, but the second derivative is 0 here, and the second derivative is 0 here. And all I need to do in this question then is pick some test points. Imagine there's a region here, from there to there I'll call A. There's another one here, I'll call that B, and a tiny little one at the end, I'm going to call it C. So the kind of test points, really doesn't matter what you like. In this region here, from here to here, I would probably choose 0. In this region here, 8, 6 pi. Okay, 4/3 will do. In this region here, I'd probably pick 2 pi. And for each one of those, I find the value of the second derivative. And you're just going to trust me on this. But this guy's positive, this guy's negative, and this guy's positive. But that's something you should double check. I believe it's correct. So now that I have a second derivative number line, I can tell you when it's going to increase. It's not increase. I can tell you when it's going to be concave up. And it's concave up when the second derivative is positive. So that's from x equals 0 to 7, 6 pi. And from 11, 6 pi to 2 pi. And I can tell you when it's going to be concave down. That's going to be when the second derivative is negative. So that's going to be from 7, 6 pi to 11, 6 pi. I can even tell you the points of inflection, and they happen to be at these guys. So it's going to be at 7, 6 pi and 11, 6 pi, and that's the x coordinates. And to find the y coordinates, I go right back here and I plug in 7, 6 pi and then 11, 6 pi. And you're going to trust me that when you do that one, both answers just happen to be the same y coordinate. So that is how you find concave up and concave down. And there are 3 questions, 12, 13, and 14, where that's all you do. Very similar process to increasing and decreasing, isn't it? You find a derivative, you find critical numbers, you do a number line, you do test points. Only concave up means positive second derivative, and increasing means positive first derivative, right? So you interpret the pluses and minuses in a different way. But the math is very, very similar. So now we have our last question, where you do everything. And question 15, 16, and 17 gets us to do everything, which means find all these things and all these things. And who am I picking? I don't know. Who should I pick? Let's do this fella. So for this function, I'm going to find increasing, decreasing, local max and min. And then after that, concave up areas, concave down areas, and finally points of inflection. And I have 10 minutes to do that entire question. So you can imagine this set of homework is going to be a lot. So don't do it at 11:30 on Sunday. You'll never get it finished. First derivative. Power rule. Try and factor the heck out of this. Any factors you can see?
Left a 0 off the minus 10x there.
I wrote the wrong thing down. Oh, I see.
Yeah.
Thank you. Yeah, I did. That was quick. Right. What can I factor out now?
4x.
I hear you. That's going to leave me with x squared, take away 25. Do you recognize x squared minus 25 can be factored? What do I get?
X plus 5, x minus 5.
Are we good at these guys now? Or at least a bit warmer than we were at the start of today. Right, critical numbers. 0, -5, and 5. Agree? Because we factored it all, that was easy to find. Number line. -6, -5, -4, 3, 2, -1, 0, 1, 2, 3, 4, 5, 6. You can see I'm changing my scale. Doesn't really matter. At this point here, the derivative is 0. At this point here, the derivative is 0. And at this point here, the derivative is 0. And then do test points. That's my little invisible walls. Be a region A, a region B, region C, and a region D. So I would choose a test point in region A would probably be -6. For region B, may as well make it -1. For region C, make it 1. And for region D, choose a test point of 6. And for every single one of these 4 test points, I find out what the derivative at that value of x is. And if the answer is plus or minus is all I care about. If I do a -6, that's negative, negative, negative. The whole thing is negative. If I do it at -1, that's negative, that's negative, that's positive. The whole thing becomes plus. If I do it at 1, it becomes negative. You can check this out later. And if I do it at 6, it's positive again. Have anybody noticed that the pattern seems to be it alternates plus minus plus minus? 9 times out of 10, that is exactly what will happen. But 1 out of 10 is going to go plus 0 plus. Because it could be a horizontal point of inflection. That's why you have to do the test points. Because you know the first question, you decide not to bother. That's the one you should have bothered. Right? The other 9, it'll be perfectly correct. But the 10th one will kill you. Now, from this number line, I can then move on. So for this number line, I can now do increasing and decreasing. And it's increasing from -5 to x is 0, and from 5 forever. It's decreasing when the derivative is negative. So from -infinity, -5, and then from 0 to 5. In this question here, at -5, the derivative is negative. So that means the curve is going down the way, then it goes 0, and then it's going up the way. So that tells me that there's a local minimum at x equals -5. If I look at 0, on this side it's positive, so it's increasing, then it is 0, and then it goes negative. So that there is a local maximum. And that happens at x equals 0. And then at 5, it's -0 and plus. And that is another local minimum. And that's going to be at x equals 5. But when you do this in WebDesign, they don't want to know these numbers. They want to know the value of the function at those numbers. So for instance, the value of the function, confusing myself here because I'm looking at the wrong question, but never mind. At 0, for instance, is 2. And I don't know what it is at the other 2, but can you imagine the value? And that is the end of the first part. So I've got increasing, decreasing, local max and mins. Now, here is the first derivative. I'm now going to find concave up and concave down. To do that, I need to know what the second derivative is. Why did I use this version of the first derivative and not this nice factored version? What was the practical reason for me using this one and not using that one?
For the power rule?
Yeah, isn't it much easier to differentiate a cubic than it would be to differentiate a really weird product rule? That's the only reason. Now, in this question here, technically I should be factoring things, but I can tell you right now, there's not an awful lot of benefit to factoring this one. So I'm just going to find out when it is equal to 0. I'm going to find its critical numbers, pretty much untouched. So that means I'm going to add 100 to both sides, divide both sides by 12, which I believe gets you 25 thirds. And then I can take the square root of that, and I get that. So there's going to be a critical number at negative that fella, and another one at positive that fella. So there are two places of interest in the second derivative. Five over root 3, I think it's 1 and a bit. Let me check. Oh, I'm wrong. It's 2 and a bit. Okay. So about here is where 5 over root 3 lives. And about here is where negative 5 over root 3 lives. At those 2 points, the second derivative is 0. And all I now do is some test points. Oh, this is going to be fast. A test point of negative 4 for this guy. In this region, I'm going to pick a test point of 0. And over here, test point of 3. And I'm going to find the value of the second derivative at those test points. Right. The second derivative is essentially this guy. If I plug in negative 4, it's positive. If I plug in 0, it's negative. And if I plug in 3, it's positive. And you can check that. There. Positives, negatives, positives. So I can now finish by telling you when it's concave up. It is concave up when the second derivative is positive. So that's going to be any value of x from negative infinity to negative 5 over root 3, and then from positive 5 over root 3 to infinity. And it's going to be concave down between here and here. And these two guys here, these are the points of inflection. The points of inflection are, these are the coordinates. And I need to find out what the y coordinate of that particular guy is. And I don't know. But don't I just go up here and plug in negative 5 over root 3 and get an answer? And then I put in plus 5 over root 3 and I get the other answer. So made up numbers, negative 42 and positive 42, because I like 42. But you'll find out what the real answer is. I think that question is probably going to take you about 15 minutes or at least that. And say hi and bye-bye.